this video, we're going to talk about another method for solving systems of equations algebraically, and this method is called elimination. Consider the following system of equations: x equals 6, y equals 4. Well, this isn't a very exciting system of equations. There's nothing really to solve. It's already solved. We know x is 6 and y is 4. We could graph this. It would be a vertical line and a horizontal line, and they would clearly intersect at the point 6, 4. Here's something I want to show you with this very simple system of equations. I'd like to add these two equations. Let me write it this way. I want to see if you have two equations that are true for a system. What happens when you add them? Is it still true? I'm going to add them by adding each side of the equal sign. X plus y on my left-hand side. And on my right-hand side, 6 plus 4, which I can simplify to 10. So my addition gives me a new equation, x plus y equals 10. And since we know x is 6 and y is 4, 6 plus 4 is 10. So this is indeed another true equation. If we add two equations in a system, we get another true equation. That's what I want to develop here. If we add two equations in our system, we get another true equation. We're going to use this fact to solve some more complex systems of equations in a way that will allow us to eliminate a variable. We'll use addition to eliminate a variable to create an equation that we can solve. Let's solve this system. 5x minus 2y equals negative 16 and negative 5x plus 4y equals 22. I'm going to add these. We established should be true that if we add two equations in a system, we get another equation in that system that's also true. If I add them, look what's going to happen. 5x minus 5x, that variable is going to disappear. Negative 2y plus 4y is 2y. And on my right-hand side, negative 16 plus 22 is 6. I've created what should be another true equation. And this true equation is an equation in one variable because my x's were eliminated. If I solve for y, I've got the y value of my ordered pair solution. Just like with our substitution method, once we've got one of them, we can go back to either of these equations to find x. Maybe I'll go to this top equation. 5x minus 2 times my y value is 3 should equal negative 16, and now I can solve this for x. I'll add 6 and divide by 5. That gives me an x value of negative 2. My ordered pair solution here is negative 2, 3. We can do a quick check. In my equation, 5x minus 2y equals negative 16. If x is negative 2 and y is 3, I want to check if this is true. That's negative 10 minus 6, and yep, that's negative 16. And we'll check the other equation, negative 5x plus 4y equals 22. If x is negative 2 and y is 3, does that equal 22? That's 10 plus 12, which is indeed 22. Looks like a good solution. So again, our method was to add the two equations, which had the results of eliminating x, and we were able to find y. Let's try that on this one. I want to solve this system. This time, if I add the two equations, it looks like I'm going to be able to eliminate y. So yeah, that should work just as well. This will give me an equation in just x, and I can solve for x and go back to either equation. Maybe I'll try the second one this time and solve for y. If x is 2, 10 plus 4y is 6. 4y is negative 4, which would give me a y value of negative 1. 2, negative 1 is my solution. I'll leave the check to you on this one. Let's take a look at this. I've got a system of equations. If I try this new elimination method by adding equations, I get 7x minus 2y equals 12. A little bit of a problem here. That didn't really help because I didn't eliminate x or y. This is another true equation, but it's not getting me any closer to a solution to this system. Let's try something different. I want to be able to add these two equations in a way that eliminates a variable. There are more ways to make new true equations, right? If I multiply both sides of an equation by the same number, for example, I get another true equation. Here's what I'm seeing. If I want to say eliminate these y's, I could multiply the second equation on both sides. It'll be true as long as I do it on both sides by 3, and that would create a 3y that when added to negative 3y would eliminate my y's. So here's what I'm going to do. I'm going to take my second equation and rewrite it by multiplying both sides by 3. Then my system is 4x minus 3y equals 5, and 9x plus 3y, got to distribute that, equals 21. Now when I go in here to add my two equations, 13x plus 0y, my y's are eliminated, equals 26, and I can solve for x. So it could be that we need to multiply one of the equations on both sides by something in order to be able to eliminate one of those variables. I'll go back here and try to find my y value. 4 times 2 minus 3y equals 5. That's 8 minus 3y is 5. If we subtract 8, negative 3y is negative 3, which tells me y is 1. I'll leave the check to you. Let's try this one more time. And if I were to add these, I wouldn't eliminate x or y. I want to think about maybe multiplying one of the equations by something in order to create something I can eliminate. It's much easier if one of the coefficients is a factor of the other. Then I just have one simple multiplication to do. So I could do this a couple of ways. I'm noticing right here, if I multiply 4x by a negative 2, I'll have negative 8 as my coefficient, and I'll be able to add and eliminate my x terms. If you want to, you could eliminate the y terms. We just have to either multiply one of them by a fraction or maybe multiply both of them by a number. It definitely looks like our easiest route here is to multiply our second equation by negative 2. But we do have some flexibility here. This is going to make my system 8x minus 5y equals 9, and negative 8x plus 6y equals negative 12. Now when I add them, my x's disappear. I get just a 1y equals negative 3, so I get my y value right away. And I can plug it back into either equation. Maybe we'll go into this one. 4x minus 3 times negative 3 equals 6. That's 4x plus 9 equals 6. Or 4x equals negative 3, which gives me an x value of negative 3/4. Again, I'll leave the check to you. This one is a little bit trickier. I'd like to eliminate either x or y, but I'm not seeing a single multiplication that will do it. Those coefficients aren't factors of one another. In this case, I would make a choice. Do you want to eliminate the x's or the y's? And then I would multiply both equations by something in order to get a common coefficient. Let's choose eliminating y's. One is positive and one is negative, so I like that choice just so I don't have to multiply by a negative and potentially make more mistakes. If we multiply the top equation by 5 and the bottom equation by 3, both of those coefficients will be, well, negative 15 and positive 15. So let's try that. Multiplying both equations this time. It gives me 20x minus 15y equals 65, and 21x plus 15y is negative 24. This time when I add those, my y's disappear. I've got 41x equals 41, so x has to be 1. We'll plug it back in to get y. 7 times 1 plus 5y is negative 8 was my original equation. if I subtract 7, 5y is negative 15, or y is negative 3. I'll leave the check to you. What's important to notice in this example, we had to multiply both equations by something in order to have a coefficient that would cause one of the variables to be eliminated when we add. Let's check out this system. Looks a little simpler again. I'm thinking if I want to eliminate, say, the x's, I could just multiply this top equation by a negative 2. That would give me negative 2x minus 2y is negative 20, and 2x plus 2y is positive 20. And you can probably see what's going to happen here. The x's and the y's are eliminated. We end up with 0 equals 0. When we studied the substitution method, we had some algebra that led to something like this. We talked about how if it's a true equation, that means it kind of doesn't matter what x and y are as long as they satisfy either equation. It's going to be another solution to this system. It must be the case that these are dependent. They're actually the same line, and there are infinitely many solutions. In fact, if we look back at this, we can see the first equation doubled gives me the second equation. They are exactly the same. So this system is dependent. Here's almost the same system, although if we double the first one, I don't think we get the second one. That constant is different. If we try to solve this using elimination, I might again try multiplying the top equation by negative 2. And I think we'll see that the x's and the y's both end up eliminated. But negative 6 plus 20 is 14. We get something that is false. Our conclusion here is there's no solution. These must be parallel lines. If you wish, if it's helpful, you can write these both in the form y equals mx plus b. You'll see that they have the same slope but different y-intercepts.